Hello everyone. In this video, I want to talk about double pendulum and another interesting thing about it, which is chaotic motion or chaos. So the word chaos that you might have heard in real life in dynamic systems is basically a different thing. Now you might say, well, chaos means disorder or lack of ability to predict. That's kind of true, but what we are talking about chaos in a dynamic system, we are talking about what? We are talking about deterministic systems. So the equations of the motion are completely deterministic. There is no randomness in the system as we're going to go and derive the equations governing for a double pendulum. You see, there is no stochastic parameter. There is nothing that we don't know. Everything we know, all the parameters, every part of the equation, and the system does not need to be super complicated. Okay, so the system does not need to be complicated. So you might say the reason that the system is chaotic and is hard to predict its future is because the equations of motions are very complicated. Now, in case of double pendulum, when you look at these equations, you might say, well, they might be complicated. And that might be true, but there are systems that are, the equations of motion for them are much simpler than this, yet they still show what? They still show chaos. And that equation could be as simple as x double dot minus mu times 1 minus x squared times x dot and then plus x equals 0, which is a simple second order system. It's nonlinear, and the damping term in it is basically a combination of velocity and position. This system here, which is one of the well-known systems in chaos, is what we call the van der Pol oscillator, and that is the topic of my next video. There is something interesting in this guy called the limit cycle, so I'm gonna simulate that for you. And you'll see, so the equation does not need to be really complicated. Even simple systems can have chaos in them. One other thing is definitely the system has to be nonlinear. So linear systems will never show chaos. The system has to be nonlinear. Nonlinear systems are interesting. They show kind of behaviors that you will never see in a linear system. One of them is chaos, the other one is this limit cycle, and so on, and we're going to see them in this video, a few of them in this video, and the other bifurcations. There are so many interesting things in them, but definitely system has to be nonlinear, although the equations do not need to be very complicated. And here we are talking about deterministic systems. Now, one of the important thing about this chaos is, what is chaos? So does chaos mean that I cannot predict really what kind of motion does the system have? No, it's not necessarily that. I mean, here, if I have these governing ODEs and I have some initial conditions, and here is double pendulum under its own weight, so there is no external torque, no damping, no nothing, so it's sustained oscillation, okay? And if I let a double pendulum from some initial conditions, theta 1 of 0 and theta 2 of 0, and let it move, can I exactly know what is the location of these two endpoints at any point? Yes, I can. But the problem is sensitivity to initial conditions. Okay, so let me add that for you here. That the system is sensitive to initial conditions. I mean, if I start system from one condition, it will behave one way. If I start it from very, very close initial condition to the previous one, just slightly different, the behavior is going to be completely different. And that's not what you expect in a linear system. I mean, if I have a basically simple mass spring system, right? And here, this is M, this is K, this motion is called X. And you know that the equation of motion for the system is mx double dot plus kx equals 0. And if you release it from x0 equals some x naught and x dot 0 equals 0, right, and you release it from rest, you know that the solution here, x of t, is going to be basically x0, and then you're going to have cosine of square root of k over m times t. Okay, and this guy is called natural frequency. This is square root. And now the thing is, if I change this x0 to like 1.01 times x0, then what you will see is basically initially you had this cosine behavior, right? You have this behavior, something like this. Now, if I started with a slightly bigger amplitude, you're going to see very similar thing. The same frequency, a little bit bigger magnitude. And here is exaggerated, but let's say. So the behavior is not going to be much different than previous time. It's a linear system. I change my initial condition slightly, 1% increase in the starting amplitude, and the behavior is going to stay very close to what? Very close to whatever it was. And it's going to keep like that all over the time. Okay, so as time goes forward, this difference between these two signals stays the same way it is. Okay, and it's not going to change. That is a linear behavior. But in a nonlinear system, here I start my initial condition slightly different, slightly, like this green one, okay, slightly different, but instead of staying very close to that one that was x0, now this 101 x0 is going to go something crazy like this. Okay, and the distance between the between the orange and the blue curve is going to increase over time. Is going to increase. What kind of increase? Exponential increase. So this difference between them is going to be what? Exponential difference. Okay, and the power of that exponential, if you show it with letter lambda, okay, that lambda here is an important parameter that in chaos theory we call it the Lyapunov exponent. So two responses that came from two very, very close initial conditions over time, they get their distance bigger and bigger. They separate from each other in an exponential way where that power we call the Lyapunov exponent. And that is an interesting thing. Probably all of you heard the term called the butterfly effect. Okay, which kind of we say it's like if a butterfly flaps the wing in somewhere way off of the coast of USA, like maybe in South America or somewhere else, then that flapping can change the weather tomorrow from what I expected it to have tomorrow to something completely different. Okay, so that butterfly wing flapping is that small change in the initial condition for weather, because it is determined that weather patterns are chaotic. One of the systems we have in nature that are chaotic is weather. So we don't need to look at double pendulum. We can look at weather, and you probably have seen many times when they try to predict the weather, whatever they predict and whatever you see in real life, they don't match. Why? Because they look at some initial conditions for tomorrow based on the weather, and based on that they predict, hey, today is going to be sunny, for instance. But then some small things change which they cannot predict it, and that small change make your weather to be what? Cloudy or rainy even, although that was not expected. So it's this sensitivity to these initial conditions that makes chaotic systems hard to predict. If I knew my initial conditions perfectly, then there will be nothing to be undetermined or hard to predict. The problem is these initial conditions. In reality, these initial conditions, how do I set them up? So here, if it's double pendulum, I try to set up these initial angles, theta 1 of 0, right, and theta 2 of 0. Let's say the velocities are 0. We release them from rest. We bring these pendulums, two of them, pendulum 1, pendulum 2, to these two angles and then release them, right? And then we look at the behavior of this double pendulum, which I wrote a MATLAB code and I'm going to show you. But in reality, how accurate can we set up these angles? Can we set them up infinitely accurate? So if I want this guy to be 30 degrees and I want this guy to be 45 degrees, can I have all these future zeros in them, right? Can I have all these zeros perfectly determined? No. Our sensors, our systems have limited resolution and limited accuracy. So although one time I expected it to start at 30 and I simulated the behavior, in reality, instead of 30 perfect, all 0, 0 forever, one of these zeros becomes a 1. So it becomes 30.01. Then I say, well, that's just 0.1 of a degree. If that is changing, and I don't even know that I set it at that because my sensor cannot measure that much, that small fraction of an angle. And then I see, oh, look, last time I started at 30 and 45, I kind of saw some behavior for this pendulum, right? Let's say if I trace these endpoints, if I attach a pencil and trace the endpoints, this time, again, I started at 30 and 45, but it showed me a completely different pattern, this endpoint. How come? I started the same exact initial condition. How come it's different? No, you didn't start the same initial condition. Last time it was probably 30.02. This time it's probably 0.01, and your sensor cannot go to 100th of a degree, so you cannot see this difference, but the physical system does. And you see completely different behavior, although these two initial conditions are clearly so close to each other. That is chaos. So let me show you what happens in a physical system. So what we do here is we are going to look at the double pendulum. Double pendulum is one of the systems that the presence of chaos in it has been approved, and I'm going to show you a demo of that today here. So you can see that. So here the mass and the length of the members are both M and L. If you want, you can have them different, M1, M2, L1, L2. And the members are continuous, rigid bodies, so they are not like previous examples of pendulum where I concentrate all the mass at one point, although even if you do it that way, still it does have chaos in it. So it doesn't matter whether it's concentrated mass or continuous mass. But for the sake of making it different from previous videos, I made these pendulums rigid bodies with a distributed mass. And I made them to be same mass and same length. It's not going to affect the nature of the system. So the centroids are in the middle of each member. The angles are both measured from vertical direction, so they are absolute angles. And here we use the Lagrangian method for formulation. The kinetic energy is going to be two terms for each member. It is going to be basically a translational term, which is 1/2 mass times velocity at the centroid squared, plus a rotational term, 1/2 I about the centroid times angular velocity squared. So we calculate it for member 1 and member 2. I about the center of a slender bar with mass m length L is ml squared over 12, as you know. Now, in order to calculate these velocity terms, we need to look at the position of these two centroid points. And if I use x and y the way I did, then x of this point C1 is clearly this distance, which is L over 2 times sine of theta 1, and y of it is this distance, which is L over 2 cosine theta 1. Since it's below the axis, it has a negative. And similarly, this point C2 is going to be this distance plus this one, the x of it, where this distance is clearly the whole L times sine theta 1 plus half L here times sine theta 2. And then for the y of it, again, it's going to be a similar thing. So it's going to be this distance, which is negative L cosine theta 1 plus this one, which is negative L over 2 cosine theta 2. Now you take time derivatives from these x's and y's, and you can find x dot and y dot of C1 and C2. You can square them and add them together to get those velocity terms squared. And if you do some simple algebra, you can simplify what? You can simplify the velocities to be these guys in terms of the 2 degrees of freedom, theta 1 and theta 2. Okay, so these are the velocity squares. So now I can have my entire kinetic energy formulated in terms of the angles and velocities. For potential energy, it is going to be negative mgy of point C1, negative mgy of C2, which if you plug in this yc1 and yc2 in it, this is going to be your potential energy. So now you subtract P from K, you get the Lagrangian. And if you simplify Lagrangian, this is going to be your Lagrangian, this guy here. And now what you need is you need to find 4 partial derivatives. Partial of Lagrangian with respect to theta 1 and theta 2, as well as partial of it with respect to theta 1 dot and theta 2 dot, and plug them into the 2 governing equations. So for instance, I calculate a couple of these terms for you. So if that is my Lagrangian, let's say what is the Lagrangian of L with respect to, let's say what? Theta 1 dot. Okay, let's calculate that. What is it? So you have this term here, that is a 4 over 6, and that 2 will come out, so it's going to be 8 over 6 or 4 over 3. So it's going to be 4 over 3 m L squared, and then theta 1 dot. Theta 1 dot, yes, that's the linear term. This term here, that 3 over 6 is going to be 1/2, and it's going to be the rest of it. So it's going to be 1/2 mL squared, and then theta 2 dot times cosine of theta 1 minus theta 2. Or let's say you want the partial of L with respect to theta 2, huh? This term here. What is that? Well, all of these dot terms have nothing except for here. So that theta 2, the negative comes out. Derivative of cosine is negative sign. Those 2 negatives would cancel each other. And all of this rest of the term, which is going to be 1/2 mL squared, and then theta 1 dot, theta 2 dot, and then sine of theta 1 minus theta 2. And here again you have this term, which is going to be negative 1/2 mgl and sine of theta 2. Okay, and similarly you can calculate the other ones, and then now you have to take time derivatives from these. So when I take time derivative of this, right, let me just take time derivative of this one for you so you can see that. Let me clean up a little bit so we can move forward. So let's say if I want to take what? I want to take time derivative, huh? So what is time derivative of this guy? So it's going to be 4 over 3 mL squared theta 1 double dot. And here you have 2 terms that is a product. So it's going to be mL squared over 2 times derivative of theta dot times cosine. So it's going to be theta 2 double dot times cosine, and plus theta 2 dot times the derivative of cosine. And what is the derivative of cosine? Well, the derivative of cosine is going to be both of these guys, their time derivative coming out with a negative, and multiplied by theta 2 dot. So it's going to be plus theta 2 dot times negative sine times theta 1 dot minus theta 2 dot. If I multiply that negative by theta 1 dot minus theta 2 dot, it becomes theta 2 dot minus theta 1 dot, and then sine of theta 1 minus theta 2, like that. Okay, so that is going to be the derivative of this one. And you can calculate the other terms and plug them in. The last thing you need to calculate are these generalized forces or torques for them. Since they are angles, these are generalized torques, both of them. Now, is there any torque applied to theta 1 or theta 2 from outside? The answer is no, nothing. Here, you don't have any external torque applied to any of these angles. Therefore, your Q of theta 1 or Q of theta 2 are 0. If you had a torque here applied to any of these joints, like what? Let's say like this one. If you had a torque T1, right? Or if you had friction here, like constant C times theta 2 dot, then they will be these things, right? So in this case, if I had this one and that one, then this guy is going to be negative C times theta 2 dot, and that guy is going to be T1. But in this case, I don't have any of them, so in this case, they are both what? 0. Now, if I plug in all the terms here and I do some simplification, which I'm sure I can do, I get to these two governing ODEs. Okay, so these are the two governing ODEs. Of course, they are coupled. You have to solve them at the same time. And guess what? There is no analytical solution. So you have to solve them numerically with any numerical solver like Runge-Kutta or Euler's method. You better use Runge-Kutta to be accurate, relatively accurate. And one thing you can do is you can write this into matrix format. So it's going to be some matrix times the two unknowns, which are the double dots. This is equals to some right-hand side. And from here, you can find the double dots, which you need them if you want to write it in the state space. So here, my two m's are the same, so I can get rid of these two m's. That makes life quite a bit easier, because now this entire term will get out of the parentheses. You see there is one L theta 1 double dot here, and there is another one here. So you get 2L theta 1 double dot. For theta 2 double dot, the term is this L times that cosine. This is L. And the second equation for theta 1 double dot, again, you see it's that L times cosine of theta 1 minus theta 2, and for theta 2 double dot is simple L. Anything else will go to the other side. So here you have one G sine, another G sine, so it's going to be negative 2G sine of theta 1, and then this theta 2 dot term will go to the other side too, so it's going to be minus L times theta 2 dot squared, and then times sine of the difference. For the second equation, this negative G sine theta 2 goes down, and again this term here, which is going to be positive L theta 1 dot squared, again sine of the difference. So you write it this way, and this helps you to write the system in state space. So here the parameters I choose, the vector I choose for my state space is going to be theta 1 dot, theta 2, and theta 2 dot. Therefore, my z dot vector is going to be what? Well, this guy is z1, right? This theta 1 is z1. So derivative of z1 is the theta 1 dot or z2. Derivative of theta 1 dot or z2 dot is going to be this guy. And derivative of theta 2 dot z3 is z4. And derivative of z4 or theta 2 double dot is going to be this one. So if you solve here, if you solve and find the solution, right? So you have to solve for these two. Once you find it, you're going to have some function here in terms of theta 1 double dot, and you're going to find some function in terms of what? Theta 2 double dot. Okay? And that is all you have, and that is what you can use with Simulink or ODE45 or anything. Especially in this case, we're going to use ODE45. So in this case, the left-hand side, when you want to solve for them, the left-hand side, this is going to be L cosine of z1 minus z3. The same thing here, the left-hand side. And the right-hand side, negative 2g sine z1 minus L, this is z4 squared, sine of z1 minus z3. And then negative g z3, and this one is z2 squared, and again z1 and z3. Okay, and then these double dots are going to be inverse of this, whatever you want to call it. In my code, I call it matrix A, and multiplied by this one, which I call the right-hand side. So that is going to be A inverse times the right-hand side. And the first element is going to be what? Is going to be theta 1 double dot. The second element is going to be what? Theta 2 double dot. Okay, so here you can grab this and bring it right there. And you can grab this one and bring it right there. And there we go. You got your system. And you can, as I said, pass it to ODE45 and solve for it. So let me show you my MATLAB code now. So this is the code I wrote for it. And again, I let you download and play with this guy here. I chose the mass of both of my members to be 1 kilogram, although the mass has no role really. Because these two masses, remember, you get simplified, and so mass plays no role in this pendulum. Okay, so I can get rid of it. If the masses are different, you need them. But if the masses are the same, they will be canceled. What you need is the length of each pendulum, which I picked 0.5 meter for each. And then here, you see that I wrote a function called double pendulum, which I passed to ODE45 with the time, which I go simulate for 40 seconds, and with the vector of initial conditions. And the function that I use for ODE45, you see, it has 4 elements for vector z dot. And this is that matrix A. This is that right-hand side that I showed you. Q double dot, which is theta 1 and theta 2 double dot, is inverse of A times right-hand side. Now you see z1 is z2. z2 dot is the first element. z3 dot is z4. And z4 dot is the second element of Q double dot. Okay, so I use this function with ODE45. Now here, look, one time I run it with initial angle for theta 1 at 135, the same with theta 2, 135, and the velocity is both 0. Next time I simulate it again, this time with 133 degrees, 33.3 for both of them. So less than 2 degrees difference in the initial conditions. That's all I do. Instead of dividing by 4, I divide by 4.05. The angles are slightly different, less than 2 degrees, both of the angles, okay? And here I create animation for you. So all of this code that you see is the animation. So I animate both pendulums with different colors, and let's run it. Look. So one of them is red and blue, the other one is black and green. See how closely they started, right? Now look at how different they behave over time. And their differences get bigger and bigger. Look at that. The green one is just doing the flipping back to back. The blue one just started. So they're now look, they're making M shape and V shape. They started almost at the same point. You see how much different they are behaving now? That is not what they started with. Their changes are, the difference between them is growing. And that is this formula that you can see here, okay? That the difference between these two z's, if I call it delta z, z1 is the state vector for the first pendulum, the second one is for second one, the difference I call it delta. The difference for them over time is going to be the initial difference they had times an exponential term. Well, that power lambda, I call it what? The Lyapunov exponent. And here you see the initial conditions here. Theta 1 and theta 2 of 0 for the first pendulum are 135, for the second one are 133.3, and look at complete different behaviors that they are showing. And if you want, we can add a point at the end of these endpoints here. So you see the curve that the endpoints also plot for you, if you want, are going to be completely different curves, although we started what? Quite a bit similar. And you might say, well, maybe your conditions were not very similar. 133, 135. You have 2 degrees. Make it less than a degree or so, and let us see that. Fine. So here we make it 4.01. Okay? And let's see how much degrees this guy. So it's this one, and multiplied by 180 divided by pi. 134.66, huh? Okay, here. Yes? So now I make the difference what? Less than 0.4 of a degree. Yeah? And they should be very similar, right? But look what happens. So here I do the plot, and then I pause for 1 second so you can see it, or maybe 2 seconds, and then I start the animation. Okay, look here. You see? You can barely distinguish them from each other. Now look. Look at them. Now, of course, this time it takes a little bit more time for them to be much different. The Lyapunov exponent, that delta, is not going to change. Visually, it takes you a little bit more time to see big differences, but now you can clearly see that. Look at that. Look at it. Right? Complete different behaviors. Okay? So this chaotic behavior does exist, and the system is extremely sensitive to initial conditions. It doesn't matter how close we start, we can always get them to grow exponentially different from each other. Okay? So hopefully you learned that this double pendulum, although it's not super complicated system, just 2 objects really hanging from each other and from a fixed point, depending on what initial angles we start, they can show completely different behaviors over time, and this is a chaotic system. Hopefully the video was useful to you, and I'm going to see you in the next lecture. Thank you.